Now, let's take a deeper look at TensorFlow and Keras, two fundamental libraries in the field of deep learning. In our first lecture, we discussed developing our model using PyTorch. However, since PyTorch and Keras are also extensively utilized in the industry, it's important to understand their capabilities and differences. We'll briefly explore these libraries to provide a well-rounded understanding of the tools available for deep learning development. So, the first library I learned with was Keras. However, TensorFlow, as a free open-source machine learning platform created by Google and based on Python, plays a central theme in our discussion. TensorFlow was originally developed by researchers and engineers from the Google Brain team within Google's AI organization. It came about as a response to the need for a flexible, efficient, and scalable system to build, train, and deploy machine learning models. So, we'll discuss what Tensor and TensorFlow means a little later in the lectures. So TensorFlow allows mathematical operations on tensors and automatically computes gradients, which will be discussed later, for all differentiable expressions. We'll discuss the core mathematical concept in neural networks a bit later, but it's important to understand that this library simplifies complex mathematical operations into functions that developers can easily utilize. Additionally, TensorFlow's flexible architecture not only supports deep learning models, but also broadens its utility to include other computational areas such as computational physics and large-scale optimization. This makes it an important tool in a variety of scientific fields. Notably, TensorFlow works well not just with CPU, but also with GPU and TPU, which is a tensor processing unit, enhancing the computation speed significantly. This compatibility allows developers who may not be familiar with the intricacies of GPU programming to easily leverage CUDA for their computations. TensorFlow's ability to harness the power of GPUs using CUDA accelerates the training and execution of deep learning models, significantly reducing the time required for data processing and model training phases. Okay, understanding TensorFlow, what then is Keras? Keras is a deep learning API for Python, built on top of TensorFlow, designed to provide a simpler method for creating and training any kind of deep learning model. By abstracting many of the more complex aspects of TensorFlow, Keras enables developers and researchers to prototype and iterate on their models more quickly and with less code. This ease of use does not sacrifice functionality or flexibility. Keras is fully equipped to support advanced, large-scale applications that require deep customization. So, through TensorFlow, Keras can perform distributed operations during the training phase simultaneously on thousands of machines across various hardware such as GPU and TPU. So, Keras provided an easier way to utilize TensorFlow capabilities for deep learning and other users. This capability is crucial in environments where large datasets and computationally intensive models require the use of extensive computational resources to reduce training time. To talk a little more about the history of TensorFlow and Keras, engineers from Google created libraries for non-developers to more easily utilize the hardware. In other words, the development of Keras on top of TensorFlow was aimed at providing an accessible tool for data scientists, physicists, biologists, and other professionals who may not have extensive computer science background. So, the relationship between the two is huge. So Keras was released as a library for Theano, another deep learning library, in March 2015. Theano is a deep learning library that allows users to define, optimize, and evaluate mathematical expressions using multi-dimensional arrays efficiently, making it a foundational tool in the field of machine learning. Then, in November 2015, TensorFlow was released. So, initially, Keras used Theano as the backend, but they changed it afterward. In September 2016, TensorFlow was adopted as a default backend for Keras. The reason for Keras' adoption of TensorFlow was the enhanced scalability, distributed training capabilities, and a more comprehensive suite of tools and resources for development. in line with the evolution of the landscape of deep learning. Then, Keras adding support for CNTKey and MXNet, further showcasing its versatility. In September of 2019, with the launch of TensorFlow 2.0, Keras was adopted as the official high-level API of TensorFlow. Keras made it easier for developers to use TensorFlow, which will be a little hard for non-developers. The huge part is that TensorFlow adopted Keras after Keras adopted TensorFlow as their backend. This two-way relationship developed out of a natural alignment of their objectives. Keras aimed to simplify the process of deep learning development with a high-level, user-friendly interface, while TensorFlow sought to enhance its accessibility and ease of use without sacrificing the power and versatility it was known for. So now, with TensorFlow 2.0, Keras is so integral that saying TensorFlow is essentially synonymous with Keras. So, these two, which started as distinct entities, combined into one. The integration of Keras into TensorFlow mirrors other technological collaborations that enhance functionality, such as the combination of Apache Spark and Hadoop in the big data ecosystem. Recently, the integration of Keras with PyTorch in Keras 3 marked a significant milestone, further intertwining the relationship between major deep learning frameworks. This development originated from the desire to make Keras, known for its user-friendly high-level API, accessible to a broader range of deep learning technologies and user preferences. By supporting PyTorch, Keras expands its reach and utility. Now, let's take a look at the overall software and hardware architecture. TensorFlow provides control of tensors, which involves managing hardware such as CPU and GPU. This management is crucial because it allows TensorFlow to optimize computations by distributing them efficiently across available resources. Then, Keras was introduced so that we can easily make neural networks so that we don't have to go through many struggles of developing on TensorFlow. This design allows users to focus on high-level functionalities. So Keras was a library designed to make deep learning a little easier by providing a higher level abstraction, and TensorFlow implements tensor, which is the basic concept of neural networks. It manages how the code uses CPU and GPU to describe simply, allowing TensorFlow to execute operations in the most effective way possible. Now, let's move on to PyTorch. If we take a look at the period when it was developed, TensorFlow was developed in 2015, and 2 years later, PyTorch was released. So PyTorch is a deep learning framework released in early 2017, designed to enable developers and researchers to easily create and train artificial neural network models using GPUs as well as CPUs. And to recap what these tools do, these tools were created to streamline machine learning workflows, from designing and training models to deploying them in production. Google's extensive support has enabled continuous enhancements and community-driven expansions. As we discussed before, TensorFlow and Keras were developed by Google, and PyTorch is primarily managed by the AI research team at Facebook or by Meta. There's a thing called a PyTorch forum, where the framework developers from Meta often provide direct answers to questions asked by users. In this day and age, we can initially pose our questions to ChatGPT and conduct a deeper search using Google if needed. So PyTorch is called PyTorch because there was a precursor called Torch, which was a framework created with the Lua programming language, which is often used in the field of robotics. Facebook, or Meta now, added a Python wrapper to it. Thus, the name PyTorch. So, to talk about the differences between TensorFlow and PyTorch. TensorFlow used to be the biggest player, but these days, PyTorch has become the biggest player. I can't say for all industries, but in the bio-AI field, PyTorch is the most used by researchers. And professional AI organizations mostly use PyTorch as well. The reason is because PyTorch operates on a define-by-run approach, which we'll discuss in our later lectures when we talk more about the neural networks. But to provide a brief overview, the computational graph and values are initialized simultaneously, making the code easier to understand without the need to separate the computational graph from the operations. This approach, being more intuitive than TensorFlow's earlier versions, allowed PyTorch to quickly capture a significant market share, even though it came 2 years after TensorFlow. The intuitive nature of PyTorch stems from its alignment with the way developers think and code. And this was the main reason PyTorch was able to capture the market share very easily. Unlike PyTorch, initial TensorFlow utilized a define and run approach, where the computational graph is constructed first and values are passed later during actual operations. I didn't use the initial version of TensorFlow because I used Keras, which allows us to avoid the complexities involved with it, as mentioned earlier in the lectures. Due to this difficulty, many people migrated towards PyTorch. So, TensorFlow had to make major changes to transition from version 1.0 to 2.0, not just to adopt Keras, but also to support a define by run approach, similar to PyTorch. Even though TensorFlow 2.0 has adopted a similar approach to PyTorch, I used to use Keras and TensorFlow 2.0 by default, and I had to switch to PyTorch when I changed companies. This migration process from Keras TensorFlow to PyTorch is quite complex because the syntax is slightly different, which adds an extra layer of challenges when you're pressured to produce results in a research setting. Nevertheless, I switched to PyTorch as from experience, PyTorch is a little more flexible to use than Keras/TensorFlow. Since we'll be using PyTorch, we won't go into the details on how PyTorch and Keras differ at the lowest level, but to provide a brief overview on why PyTorch is favored, the ability to adjust and optimize on the go without recompiling the entire model speeds up the development process significantly. This has attracted a large following in both academia and industry, particularly among researchers who prioritize rapid prototyping and experimental flexibility. The optimization doesn't stop here. There are libraries built on top of PyTorch, such as PyTorch Lightning, which is a lightweight PyTorch wrapper for high-performance AI research. Another example is MONAI, which stands for Medical Open Network for AI, which was built by NVIDIA. So, this is for researchers in the medical field, which is based on PyTorch. By utilizing this network, researchers gain access to pre-built, high-quality neural networks, which can be adapted for a variety of medical imaging and diagnostic applications. This not only saves time, but also enhances the precision and effectiveness of medical AI applications. By leveraging such advanced tools, medical researchers can focus more on clinical insights and less on the technical complexities. To summarize the differences between Keras, PyTorch, and TensorFlow, API means the level of abstraction of the libraries. So high means it mainly deals with software, versus low means it deals with hardware. So, to take a look at the libraries based on the API, Keras operates on a high layer, whereas PyTorch operates on a low layer while providing easy syntax. From the improvements it has had over the years, in terms of architecture, Keras is the simplest, most concise, and readable, which means that it's basically the easiest one, whereas PyTorch is a little more complex and less readable than Keras. And to clarify, by TensorFlow here, we mean initial versions of TensorFlow, and it was not easy to use. So, since it's been a couple years since the inception of PyTorch, TensorFlow, and Keras, they have basically covered the weaknesses addressed in this table. For example, PyTorch operates on the low level, but it has gotten simple, concise, and readable, comparable to Keras. And all these three have developed to perform well with large datasets as well as performance. Also, debugging has gotten a lot easier for all three libraries. In terms of popularity, Keras was the most popular since it was the easiest, and TensorFlow was second since it came out before PyTorch, which came out last of these. But now, the ranking has changed so that PyTorch is number one in terms of popularity. So, if you look at other artificial intelligence courses, you'll see that most of them now use PyTorch as the library of choice. In terms of speed, all three of these libraries are fast. But for Keras, since it operates on the highest layer, it is still the slowest of the three. So the characteristics shown in this table are from the past, and now PyTorch is the best overall one. So that is why we have decided to use PyTorch in our lectures. In our series of lectures, not all parts have the practical aspects, but for the ones that do, since it is hard for an individual to set up an environment. For example, GPU is needed to train the models, which I can't force you guys to buy. But to do AI without GPU is not ideal. Using CPU to train would take exponentially more time than using a GPU, and the CPU may not be able to get the job done. So, we'll be utilizing Google Collaboratory. Even though we talked about the importance of setting development environment, which is typically solved by Docker, we won't be using Docker and rather Google Collaboratory. So, just because they're Google doesn't mean we can't use PyTorch, which was developed by Meta. We can both use PyTorch and TensorFlow. So, the development environment is already set up in Colab. Not only that, but it also provides a source code editor, and it's easy to see the results. Also, it provides GPU. The only thing you need to use Colab is just the Google account. So, we'll go deeper into Colab when we do our practicals. So, Google Colab will allow machines of different configurations to run on the same development environment. To summarize what we have been talking about, we focused on understanding the basics of AI. We've explored the fundamental concepts and technologies that drive this dynamic field. First, we talked about machine learning, which is a method that enables machines to learn and process given data. It serves as a fundamental category within the broader field of artificial intelligence. Then, we delved into deep learning, a specialized area of machine learning that utilizes neural networks, specifically deep neural networks, to interpret and learn from the data. A key point is that traditional methods were not effective for unstructured data, such as video and audio. But deep neural networks have significantly enhanced our ability to process and utilize this type of data. And this breakthrough has opened up new possibilities in fields ranging from autonomous driving to medical imaging. Next, we explored how to develop artificial intelligence using Python programming, which involves 5 key steps: data collection, data processing to enhance model training, and model building, model training by inputting refined data, analyzing the results, and if satisfactory, deploying them or writing research papers. If the outcomes are unsatisfactory, we iterate through the steps until we achieve a successful model. And with that, we'll conclude our lecture on Introduction to AI.